So in this section, we're going to focus on the concept of the antiderivative. Now, this is all this really is the idea of the inverse of a derivative. So that is to say, if a derivative was already taken, this process would undo it, or we're going to do the inverse operator of the derivative. And the nice thing is we've already been talking about these a little bit. We've already been using these a little bit in section 3.2, where we were doing integration, where we're finding integrals. What we're going to do here, though, is in each of those problems, they gave us something that looked like this. They maybe said integrate from 2 to 3 of x squared plus 3x dx. And for us to be able to do this problem, they started us off with f of x, capital F of x, which was x cubed divided by 3 plus 3x squared divided by 2. In this section, we're going to figure out how to calculate these capital F's. That's it. That's all we're doing. So it's just going to be a whole bunch of derivative rules, but just instead of doing them forward, we're going to do them backward. So let's go ahead and take a look at this first problem and see how this feels. If f of x is equal to x to the fourth plus 1, find its antiderivative, capital F of x. And how we can check to see if we got the right answer is, well, once we find the antiderivative of it, taking the derivative of that should bring us back to the beginning, right? So that is the second part of the fundamental theorem of calculus, which just says the derivative of an antiderivative of some function just leaves you with said function, right? Just the integration will do something, but the derivative will undo it, putting you right back where you started. Okay, so if f of x equals x to the fourth plus 1, can you find capital F of x? Now, go ahead and pause the video, try to think your way through it, logic way through it, and say, all right, this is the answer to the derivative, so what did I start with? All right, pause the video, give it a shot. Okay, what I'm hoping you came up with is you said, okay, well, the first rule we learned was the power rule, which said something like if I had x to the fifth, then the derivative of that would bring the 5 out to the front, and we'd subtract 1. So therefore, instead of subtracting 1 from our exponent, we would be adding 1 to our exponent. And then instead of bringing the number out to the front for multiplication, now we're going to be dividing. And you may not have quickly jumped at what this number is down here, so I'm going to just put a 5 because I know what it is. And then I will kind of show you what's going on here. Then the derivative of 1, well, remember that's really times x to the 0. So if we add 1 to that, that'll make it x to the first divided by 1. And what we're going to see here is, well, we can verify this by taking the derivative. If I do the derivative of this function, if I say what is what is f prime of x, and remember the notation we covered is, well, we can just change that to a lowercase f of x. Well, the derivative, say, bring the 5 out to the front, which would make it 5 times x to the fourth divided by 5. Perfect. Those 5s divide. Then plus x to the first, whoops, didn't want that in red, x to the first, so therefore bring the 1 out to the front, subtract 1. And then we were dividing by 1, so those 1s would divide, leaving us with x to the 0. And x to the 0 is 1. So it worked. That was our antiderivative. So looking for that pattern, saying, okay, instead of subtracting 1 from our exponents, we're going to add 1 to our exponents. That's that part usually not too bad. But why dividing by 5? Why dividing by 5? Why not first divide by the exponent, make that a 4 down there, then add 1? Well, it's inverse order. It's the exact opposite. Think about what we used to do, right? The operator used to be, if I did the derivative of something to the fourth, I bring this out to the front, then subtract 1, right? So the order was first multiply by your coefficient, then minus 1. Well, if we're going backwards, therefore we have to start by, instead of minusing 1, we start by adding 1. Then we will divide by whatever that number was. So looking at this next problem, before we move on, actually, and you can see that idea why it works out, because in the original problem we start with a coefficient of 1. So when I do the derivative, whatever that exponent is, needs to come out to the front. And I need that number, if it's a 5, I need it to be dividing by a 5, because 5 divided by 5 would bring me back to my original 1 that I started the problem with. So that's the other reason you can see why we need that 5 there. So looking here. All right, find the derivative of this function. Can you find the derivative of this function? Not the integration, just the derivative. All right. Hopefully you don't have to pause your video too long for that one. The derivative would be 3x squared. Right. So notice we bring the number out front, then subtract 1, minus bring the 2 out to the front. X subtract 1 divided by 2 plus 1 plus 0. Okay, and then what kind of notation should we put in the front? Because we did the derivative of f of x. That would be the same thing as f prime of x. But as we know, we can now use that lowercase notation, and there we go. All right, so now, using your answer from the previous problem, we know f of x equals 3x squared minus x plus 1. Can you use this to find the capital F of x? Okay, try to go backwards. Now, obviously, yes, I know. You can look back at the previous answer and get your answer to this. Don't do that. Try to come up with it on your own. Pause the video, give it a shot. Okay, so here we go. When we do this integration, we say, okay, first thing I need to do is add 1. So it goes from x squared, I have a 3, it goes from x squared to x cubed, and then I'm going to divide by 3. Then I'm going to raise this x squared, and I need to divide by 2. Now, yep, that's perfect. Okay, so then now I have 1, all right, and remember that's really x to the 0, so I got to add 1 to that. So that's going to make it plus x, and that's all we got. So did this bring me back to the original problem that we started with? It didn't. Something's missing, right? Because 3 divided by 3, all right, so we can clean this up a little bit to make it easier to see. So this gives us x cubed minus x squared divided by 2 plus x. So you can see our x cubed term and our x cubed term match up perfect, okay? Then I've got my minus x squared divided by 2, minus x squared divided by 2, beautiful. Then I got my plus x, I got my plus x. What don't I have? My constant. Well, that kind of makes sense, because if you think about it, the derivative of a constant is 0. So when we're going backwards, how would I ever know if there was a constant there or not? I wouldn't. So what we're going to have to do is, whenever we do an antiderivative, we're going to have to put a plus c. We're going to have to add on, saying there's a constant there. There could have been a constant there. When I did my antiderivative, and I got back to my original problem, there could have been a constant. There might not have been a constant. So I'm just going to put a plus c, and this number could be anything, any real number. And so therefore, if there wasn't a constant, then that thing's 0. And there you go. So how is this related to the meaning of the integral? Well, if we go back to the meaning of an integral, if you go back and think about an integral, what is it saying? Well, it's saying the area under the curve, right, is equal to some function. And the function we had in this problem was, what, 3x squared minus x plus 1 dx, right? And we would always have it going from some value, 0 to 4 maybe. So can we now do this? Can we now do this problem? All right, so how would we do this? Well, we need to know what the capital F of x is. We need to know how to, oh, we know how to do that. It's right up here. It's right there. Okay, so therefore, I'm going to take these values and sub them in. So the antiderivative would be x cubed minus x squared divided by 2 plus x plus c, evaluated from 0 to 4. Okay, so then I'm going to say this is 4 cubed minus 4 squared divided by 2 plus 4 plus c minus 0 minus 0 plus 0 plus c. All right, and that just, if that was too fast for anybody, that I was just taking 0 and subbing in for x, and 0 cubed is 0, right? X squared, so 0 squared is 0, even though it's divided by 2, it's still 0. So anyway, you'll notice here, not much has changed, except, excuse me, you may be noticing I've got this c on this side, and then I'm going to subtract a c on this side. So kind of the cool thing here is does the c even matter when we do one of these problems? Does the constant really matter? Well, no. And it kind of makes sense that it doesn't, because if you think back to change, if you think back to what a definite integral means, it's talking about the change. So when we were talking about like change in time when we were driving, like you might have some kind of cool equation saying you're going 65 miles an hour, and you started 15 miles an hour and 15 miles away from your house. Well, if I'm asking you how far did you go between your third hour and your fifth hour, well, this 15 doesn't matter, because the only thing that matters, your initial distance away from your house isn't affected by the 3 and the 5. Well, it is, but they're both affected by 15. I traveled 65 miles an hour for 3 hours and my original 15 miles. Then I traveled 65 miles an hour for 5 hours and my original 15 miles. So when I subtract these, right, when I subtract one from the other, I'm going to have 65 times 5 plus 15 minus 65 times 3 plus 15. So you can see right here, when that distributes through, this negative sign and the 15 is going to subtract with that 15. The original amount didn't matter. So when I'm doing integration, if I have a definite integral, if I am integrating from 0 to 4 or some number to another number, these c's are unimportant. I don't need them. So I don't ever write them again unless I am not doing a definite integral. If I'm doing an indefinite integral, if I'm integrating over bounds which I do not know, then the c is very important. Or if I'm doing something for another person where they just say, hey, the derivative's been done, can you do an antiderivative? Well, then it's really important to include that c, because you don't know what they're going to do with it. Maybe it is important that they're aware that there could have been an initial value. Okay, so the c is important in every context other than definite integrals, where we're integrating from a number to a number. And in that scenario, we do not need the c. All right, so here we go. Now, just some practice. You take a shot at number 4, pause the video, see how you do. Okay, now what you will notice here, this is a indefinite integral, right? There is no bounds of integration, so we don't know what we're doing with this problem, so the c is going to be important. So if you did the problem and you're missing a c, make sure you add a plus c to your page. Okay, so here we go. This, it looks to me, if the derivative rule would just be a plain old power rule, so the integral would be the plain old power rule. So what was that rule that we just kind of came up with before? I add 1 to my variable, add 1 to my exponent, divide by that number. Minus, okay, add 1 to my exponent, divide by that number. And I need to have a plus c. There we go. So there is our antiderivative. And it seems like, are we coming up with a power rule that we're comfortable with? Does it seem to be working? Well, how can we check? Can you do the derivative of this? So let's say that this is capital F of x. Can you find capital F prime of x? Well, the derivative of that, bring the 4 out to the front. So we can always check our work on all these problems, which is kind of nice. And then that's a constant, so it just becomes 0. So it divides. Hey, look at that, x cubed minus x. Perfect. Okay, so yes, our answer looks good. Our answer looks very good, other than I just erased my 4. Okay, so something like that would be your answer. Okay, so try number 5. Remember, just like power rule. How do we do this? All right, well, oh, and pause the video. Give it a shot. Okay, so how do we do something like this? Well, it's really tricky. It's quite tricky. What we have to say to ourselves is, I have to rewrite this. Well, it looks like a power, right? That was how we did this in the olden days, back when we were doing derivatives. Okay, so I'm going to write this as x to the 1/2 dx. And now it looks just like the previous problem. So the integral of this would be what? I need to add 1 to a half. So 1/2 plus 1, well, then I common denominator, so that'd be 2 over 2. So that what makes what? 3 halves. Well, if it's x to the 3 halves, then I need to divide by 3 halves. And of course we need plus c. Now, some of you might be saying, that doesn't look good having compound fractions. I agree. So therefore, if for those of you, I'm going to do this once just to help you see it. It's x to the 3 halves divided by 3 halves, and plus c. How do you divide fractions? Well, it's 3 halves times, multiplied by the reciprocal, 2 over 3, plus c. So therefore, what am I going to be left with here? 2x to the 3 halves divided by 3. And if you want, you can see that this is x to the 3 halves over 1. So we multiply straight across, plus c. And that would be my capital F of x. That would be my antiderivative. Let's get rid of that. I didn't like that. Try that one more time. There we go. All right. So power rules. Okay, great. We're pretty good at those. Oh my goodness. Our absolute worst nightmare. How do I integrate e to the x? Well, think back to your derivative rules. What did we do? If that's the answer, what did we start with? If we have e to the x, oh, that was the easy one. The derivative of e to the x is e to the x. So, hey, it's the easy integration too. The integral of e to the x is e to the x plus c. All right. So on to something far more interesting. All right, here we go. The integral of 3 to the x. Well, let's think back. What is your exponential rule? What's the derivative of 3 to the x? Well, all right, that was the derivative of an exponential function was this exponential function itself times the natural log of the base. So doing it backwards, well, what is it backwards to say, okay, to integrate this, to go back from one place to the other, go from here back to the beginning. Okay, well, if I started with 3dx, I need to end with 3dx, so that's still true. And usually I multiply by the natural log of the base. Well, since we're doing things backwards, what's the opposite of multiplication? That would be division, right? And you can check it if you want. You'd say, what's the derivative of 3 to the x? That's this right here, right? So therefore, if I do the derivative of if I do the derivative of 3 to the x, then that would give me what? The derivative would give me what? The derivative of 3 to the x is 3 to the x natural log of 3 all divided by natural log of 3. Give me back what I started. So there we go. That looks good. That looks good. So there's another derivative rule. Integration rule. What is our rule for integration? It's the exact same rule for derivatives, except backwards. So the integration of an exponential function is the exponential function divided by its natural log of its base. Okay. Now, this one is a trip. This one is a trip. It's not as easy to remember. This one you got to think backwards, and sometimes you get yourself into trouble. So I'm going to do it the right way. Then I'm going to show you the trap students sometimes fall into. All right. What is this? The answer is 1 over x. What did we start with? And I will show you, if you remember, what we started with is the natural log of x plus c. So, because the derivative of natural log is 1 over the input. Now, some students say, whoa, 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 I totally didn't see that. I would have done this to it. I would have done that instead and used a power rule. Well, let's try it. If we did power rule, that says, all right, add 1 to the exponents. That gives us x to the 0 divided by negative 1. Well, x to the 0 is 1, right? So does the derivative of 1 give you this? No. Right? Doesn't work. So what's your big tip-off? What's your big tip-off that this isn't right? Well, whenever you integrate, if you have x to the 0, that would mean that this is 1 over negative 1. And just when you do a quick check of your work, you say that's not right. So it's always good. Do a 1-second check and say, no, something's not good. And your tip-off is anytime you integrate and you get x to the 0, go back and double check it wasn't natural log. Okay, that one is just, again, it's a rule you need to know. It's an integration rule that you need to know, but it's not a tough one. It's just one to recognize, right? There's nothing complicated about it. It's just something you have to recognize. And now, this problem number 9 is how we kind of catch you with that rule. Problem number 9 is how we trick you. Because we mix it in. So you see, instead of and also we don't write it as 1 over x. We write it as x to the negative 1. So if you want to, give it a shot, give it a pause, give the problem a try. Okay, so just like derivatives, when we see adding and subtracting, the rules are the same. We still say, all right, adding and subtracting, treat them as 3 individual integrations, right? 3 individual little problems. So x cubed would be x to the 4th divided by 4. All right, so then now we have to say this is 2 times x. All right, raise this up plus 1, divide by that number. Oh, and look at that, that divides. And again, here's the trap. If I were to add 1, you get x to the 0. Oh, that's the trap. That doesn't work. So therefore, I'm going to have to say that was really just 1 over x, and this would be rewritten as 1 over x, and that's just natural log. And I even wrote notes to myself over here just to warn you guys, and I totally ignored them. Boop, boop, that's not right. Note your answer will have to have absolute values. So what we're going to go ahead and do is say every time we do this integration, instead of parentheses for the natural log, we're going to use absolute values. Okay, and once again, so over here, instead of parentheses for the log, we need absolute values. And you might be saying, well, why? That seems kind of weird. And here's the reason. Think about what numbers you're allowed to substitute into this function. What numbers can be substituted into 1 over x? Well, if I substitute in positive numbers, like 1 over 5, that's 1/5, that works. If I substitute negative numbers, I don't know, -4, then that would be 1 over -4, that works, right? What number doesn't work? 0, right? So this original problem has a domain of all real numbers that are not equal to 0. And the integration should maintain that. After we take our integral, that domain should still be held. But the problem is, excuse me, I'm going to cough. The problem is that natural log's domain, if we don't have the absolute values there, if you remember that function, the natural log function has a vertical asymptote at 0, and then it looks like this. So I would now no longer be able to substitute in any value other than 0 that the original problem had. I am now only able to substitute in positive numbers. So what this absolute values does for us is it now says you can substitute in any number you want into here. Well, except for 0, because the natural log of 0 is still undefined. So, but if someone substitutes in a negative value, well, then that just turns it into a positive value, which is defined. So it's a little mathy, it's a little technical. What we're trying to do is maintain the domain of the original function. So just know, every time you do an integration and it results in a natural log, we always have to throw absolute values around it. So same thing over here. Okay? So what does that do for me? What does that do for me? That brings me to our rules. If you take a quick peek at these rules, you will see none of them really should look new, right? The exponential function rules are the exact same rules that we just did, but they're the same rules as the derivative rules, except backwards. So you can see here, a to the x, the integration of it is a to the x divided by the natural log of the base. E to the x is itself. Power rule, x to the n is x to the n plus 1 divided by n plus 1 plus c. And notice these all have the plus c's on them. And then they give you a warning on the natural logarithm. The integration of x to the -1 is natural log of x. So it's everything we just kind of ran through. And nothing much beyond that in this section. I need to get to the next section before I can really start ramping up the difficulty. But I will point out, notice every single one of these problems, because they're all indefinite, none of them have bounds of integration, we should have a plus c on the end of every single one of them. Right? That plus c is really important. See, I missed one. I knew I missed one. Right there, plus c. Okay. There we go. So, nonetheless, I think you get the idea. And then when do we not need plus c's? Well, that's when we had definite integrals, when we had bounds of integration. So now comes a little bit of practice, just a few extra little practice problems for you to do. And on these problems, some of them, actually, I think, yeah, some of them have bounds, some of them don't. So we need plus c's or don't need plus c's. But let's go ahead and give them a shot. I would recommend pause the video for each one of these, try them, and then unpause, and let's see how you did. Okay, so for this problem, did you recognize your rules? So the integration of this would be x to the 4th divided by 4 minus e to the x, integration from 2 to to 7. Now, I don't need a plus c because we have bounds. And if you want to, you can have that plus c in there, and you'll just see it's going to add and subtract away when I substitute in my values. So it's an exercise in very good notation, but totally unnecessary. Okay, so it looks like I've got something like this. I'm not going to do it with the plus c's, by the way. Okay, so it looks like I should have 7 to the 4th divided by 4 minus e to the 7th. All of that minus 2 to the 4th divided by 4 minus e squared. Okay, and let's see if this cleans up at all. This would be 7 to the 4th divided by 4. I don't even want to clean it up. I'm just going to be super duper lazy. So this would be negative 2 to the 4th divided by 4. Now that does simplify a little bit, because 2 to the 4th is the same thing as what? 2 times 2 times 2 times 2. So 2 times 2 times 2 times 2. Well, 2 times 2 makes 4, so those divide. Okay, so I will do that a little bit. E squared. Oops, sorry, plus distributes. There we go. So therefore, my final answer that I'm going to leave it as is 7 to the 4th divided by 4 minus e to the 7th minus 4 plus e squared. All right, and that would be an exact answer. So in Math AS, if they don't say it around, then that's how you would leave it, just like that. I know, ugly, right? All right, so number 11. Now, here's a fun one. This looks like it should be done using product rule. Do you know how to do product rule backwards? I don't know how to do product rule backwards. That doesn't sound like fun. So for this section, we don't have any other techniques. So to avoid product rule and just use our basic rules, what are we going to have to do? Yeah, I think you got it right. So go ahead and pause the problem, see if you got it right, and then unpause the problem and see how you did. Okay, so here we go. So hopefully you said, all right, I don't know how to do product rule. I don't know how to do the derivative of the first. Let the second thing alone. Plus, so what we're going to do is just distribute it through, right? Just let's do that and see what we get. Okay, so x squared times x makes x cubed. X squared times a negative 4 makes negative 4x squared. 2x, sorry, this would be plus, plus 2x squared minus 8x. Excuse me. Dx. Okay, so now we can do this integration. And we know this would be equal to, the fundamental theorem of calculus says it would be x to the 4th divided by 4, the antiderivative, minus 4x cubed divided by 3, plus 2x cubed divided by 3. Oh, hello, silly me. I totally should have combined like terms. And then minus 8x squared divided by 2. Okay. And then this whole thing should be evaluated from 2 to 3. All right, so just before we evaluate it, let's add those terms together. So this is what? X to the 4th divided by 4, minus 2x cubed divided by 3, and then 8 divided by 2 makes 4, so 4 minus 4x squared, all evaluated from 2 to 3. Okay. So hopefully you've got this part down, because this is just, now at this point it's just a review from last class. So 3 to the 4th divided by 4 minus 2 times 3 cubed divided by 3, and then minus 4 times 3 squared. All of that minus 2 to the 4th divided by 4 minus 2 times 2 cubed divided by 3 minus 4 times 2 squared. All right, and just out of sheer I don't careness, I just want to leave it like that. So we absolutely could start saying, okay, this is 3 times 3 is 9, 9 times, so it's 81/4. This seems horrible. 3 times 3 is 9. And actually what we could do is divide here. I've got 3, so that would make it squared. So that would just be 9 times 2. So that would be at, what, 18? So this is 9 times a negative 4. Yeah, that's correct. 9 times negative 4, so that's negative 36. So we have some like terms there that we can combine relatively easily. Minus, and let's make sure we distribute this through. So I'm actually just going to change my signs so I don't forget. Okay, so then what is this going to come out to be? 2 to the 4th. 2 times 2 is 4. And then times another, so that's 16. 16 divided by 4 makes 4. It was in blue. Plus 2 times 2 is 4 times 2 is 8 times 2 is 16, 16 thirds. Plus 2 times 2 is 4. 4 times 4 is 16. Oh, goodness. I'm just going to be lazy. I'll pop this in my calculator. And my calculator has told me, assuming I made no typos, which is not guaranteed, negative 197 twelfths. All right, double check me, let me know if that's not quite right. But what I'm really concerned about is, did you get the big idea here? And I think you guys did. Okay, so here we go. This problem. Is this one a natural log? Well, remember, the derivative of natural log, d dx, the derivative of natural log is 1 over x. Now this has the same look and feel, but it's not the same because it's not x to the first down here, it's x to the fourth. So this is just a power rule. This would just be rewritten as x to the negative 4 dx. And now we can do the problem like normal. So the integration of that would be what? Add 1, so that makes x to the negative 3 divided by negative 3, evaluated from 1 to 2. And this problem is way easier than, or maybe not easier, but way shorter than the last problem. Now, if you wanted to, you could always drop this back down. I'm a fan of moving my negative signs up to the numerator, so I don't lose track of them. So what I'd be looking at down here is 3x cubed evaluated from 1 to 2. So therefore, what does that make? What does that make? Negative 1 over 3 times 2 cubed minus a negative 1 divided by 3 times 1 cubed. And this doesn't look too bad, right? 2 times 2 times 2, 2, 4, 8. 8 times 3, negative 24. Minus a negative makes a plus. And now this is just going to be 1 over 3. And we can multiply this by 8 to get common denominators. So, and then a negative make a positive. Wait, how did I end up with a negative down there? That wasn't right. This should just be negative 1 over 24, right? Not there we go. Okay, sounds better. So negative 1 24th plus 8 24ths makes 7 24ths. Okay, so there's that answer. Over to here. Now, this one is a little bit of a trick, just to see if you're paying attention. So if you want to take a shot at it, give it a shot. All right. Now, what you hopefully noticed, that doesn't say dx, that says db. So therefore, our variable is b. So we have to do our integration where b is our variable. So it's just a power rule. Look, it's got an exponent of 1. So therefore, the integration of this would be b squared divided by 2, going from 0 to h. So therefore, all right, so this is going to be h squared divided by 2 minus 0 squared divided by 2. So therefore, we just have h squared divided by 2. There's our answer. All right, not too bad, not too bad. All right, so just we'll watch out for little things like that. They catch you every once in a while. They catch you every once in a while. All right, now this problem. This problem is again, it looks like a quotient rule, product rule, but we don't know how to do that. So stop and take a pause and see if you can find a way to algebraically work around this and get your way out of it. So it's not a product or quotient. Okay, give it a second. Okay. Hopefully you realize this falls into the little trick of the dividing by a monomial. And the idea when you divide by a monomial, the thing that usually makes it easier is break it up into separate individual fractions and then simplify. most of the time this helps. X cubed divided by x, hey, that's just x squared. X squared divided by x, so that's just x. And x divided by x, that makes 1. So by using that technique, we have now seen an easier way, I hope, of doing this problem. And now we can integrate this thing with no problem. X cubed divided by 3 plus 3x squared divided by 2 plus x. And I'm done? No, I'm not. What am I missing? This problem, we need to have a plus c. Why do we need the plus c? Why is that so important? We do not have bounds of integration. So essentially, someone just said to us, find me the antiderivative and tell me what that answer would be. So we need to make sure we tell them the x cubed would be divided by 3, the x squared would be divided, 3x squared divided by 2. All these terms would be, we know what these are. The only thing was we don't know if there was originally a constant, so we're going to put a plus c there. Okay? So, what were the big ideas from this section? The antiderivatives. Just doing the rules and being able to use them in conjunction with what we did in section 3.2. So make sure you learn these rules, make sure you get them down pat, and you'll see there's really not much going on these rules. These are just a repeat of what you did from chapter 2, just backwards. Okay, best of luck.